Good morning, everybody. I am Noura Ibrahim from the University of Michigan. I'm a fifth-year PhD student, and I will be talking to you about imaging the inner AU of rhizomes. Thank you. Perfect. Thank you so much. All right. Well, I'll start with this schematic that we've been seeing all over this conference, and I just want to make sure to just point out where I'm going to be focusing. So it will be this area right here. So we'll be looking at the edge of the dust rim here, and then the inner emission that might be coming in from beyond the dust wall. Okay, and to be able to resolve that area, we use near-infrared long-base interferometry. So I'll be using data from CHARA and from VLTI. So CHARA is the 6 telescope array on Mount Wilson here in California, and VLTI is located in Chile. And combining them provides us with enough coverage to be able to resolve those really inner disks that we're looking at. Okay, so just to recap, in case you're not familiar with what interferometry data looks like, so one of the things that we look at is called visibility, which is the measurement of the light and dark kind of ratio of the fringes that we're looking at as we're interfering the light. And it measures from 0 to 1 here on the y-axis, and then baseline down here on the x-axis is the distance between the pairs of telescopes that we're looking at. So with CHARA, we have a maximum baseline of 300, so there's 300 meters between the two most distant telescopes. So on the shorter baselines, we get this drop in visibility, and it tells us about the larger structures of the disk that we're looking at. So it will tell us about the diameter, for example, and just the general shape of it. And then as we're going to more longer and longer baselines, we start resolving the object more, and you get more information about the finer scale structures. So you can expect to see some sort of bounce, for example, if you have a sharp rim with like an inner cavity. And if you don't detect that, if it's more of a softer object like this, you'll get something that's not as bouncy. So this is one example of data. So this is MWC 275. This is what John talked about yesterday. And this is an example of data with some models behind it. So I just want to point out this dust rim model at 1800K, which is that right here. And then if you add some gas emission coming in from the inner edge right here as well. So they match pretty well as you're going in the shorter baselines, but then as you go towards longer baselines, they kind of deviate here, where you're seeing this bounce in just the dust only case. But if you add in the inner emission, you get a more of a flat line like that, and you're not recovering that bounce more. And the data here, so this is from RJ's paper in 2008, showed that there was not really a bounce and that the cavity, they couldn't recover cavity, which you can see in this image versus this image right here. You see it's kind of filled right there, which this is not what we expect, right? And then more recently, also John showed this yesterday, so I'll go over it very quickly. Data that was averaged over many years of this object as well was not able to recover this bounce and fit the best image as a Gaussian with some sort of inner emission. So it's kind of what that was pointing at. But as we know, we can't really merge dates like this, as we know that objects are really dynamic and it will blur out any of the structure that we're looking at. So before we continue this, let's just talk about what inner emission could be. So this will be the majority of the talk. So there are a few theories for what inner emission is happening from. So we could be getting hot inner gas emission from like ionized gas. So you have a hot star and it's ionizing the gas around it, and it can be optically thick due to free or bound-free opacity, which this has been seen in BE stars. If you have an A star, for example, that's less hot and it doesn't have that enough like reservoir of ionized gas, you would need some sort of local heating mechanism to be able to heat the midplane to get you more of that ionized gas. It could also be shielded dust. So if you have some dust that is shielded by optically thick gas in the midplane, it can reach farther and farther in towards the star, and you get a much narrower inner disk. And to be able to explore this more, you need to do radiative transfer modeling. I'm sure many people have in this room especially. And then the third thing that I want to talk about is looking at dust species that can exist just at high temperatures, some sort of like refractory dust that will exist between the 0.1 to 0.45 AU, usually will be in a low density regime, and it will just be able to, it's more refractory than we think, pretty much. So let's keep that in mind as we look at what's coming. Okay, so the star that I want to talk about for the rest of this talk is V1295 Aquila. It is a late B star. It's pretty luminous. It's about 6 solar masses, pretty medium size, if on the more heavier side. It has some narrow emission line features. It has weak detected magnetic fields, and it has a face-on structure, which is great for imaging for us. Okay, so these are results from the same paper that Ben did in 2018. So here on this side, oh, no. Hopefully it'll come back. It'll come back. Okay, yay. All right. Well, on this side, you're seeing data that was averaged over 10 years, which again, we know we're not supposed to be doing that. But what you're noticing is that we're also not recovering a bounce in the visibility. And the best fit that they were able to get was also a Gaussian, meaning that they weren't able to recover a central cavity. You can see maybe right here that kind of wants to bounce, but you're not really seeing that. So this was data averaged over 10 years, as I said. It has data from Chara, it has data from VLTI, but it's more older instruments. So after that, to be able to really look and study this object better, and with the upgrade in some of the Chara instruments, especially MERC-X, we're able to really get much better data and look at what this source really looks like. So these are what the newer data look like. So in the middle, in the red, you see that is Pioneer data, and then around that, that's MERC-X data taken in 2019. The two panels are 2 epochs with 1 month in between them, and they span a 3-month period. And then on top here, you have the visibility curves. The colors are showing you different wavelength channels, and you can see them there distinctly. And then one of the good things about having different wavelength channels is that we can fit them separately, which will be able to tell us something about the color and how it changes as we're modeling the object that we're looking at. And then at the bottom here, these are closure phases. So quickly, closure phases will tell you pretty much about the asymmetry of the object that you're looking at. We have closure phases that go about 20 degrees, which means that we have a pretty much asymmetrical object. And then this is just a comparison to show you the quality of the data and how it improved between the two studies. Okay, so we started modeling this object. So on top you have epoch A, and then on the bottom is epoch B. And then we fit the wavelength channels separately. And then let me try to point out and not mess it up here. So here you can notice the chi-squareds here for how good the fit that we're showing is. So 1.5 on the top, 1.7 on the bottom here. But as you can see, we're not fitting the short baselines very well with this standard model. So we made our own model that we call the double sigmoid. And it looks like this. This is the brightness distribution. So here you have, this is the inner edge, and it goes up and it goes down, and this is the functional form that we have here. So yeah, this is what it looks like, and it fits the shorter baselines a lot better right here. And you can see that the chi-square decreased significantly. Okay, and then we're looking also at inner emission. So we have this alpha double sigmoid model, where we then added this orange brightness distribution, where the inner edge here can go from 0 to 1 and add some brightness into the center. And with that, we get a much better chi-squared as well, showing that we actually are recovering some inner emission from this object. And then from the study, and since we're able to look through the different wavelengths and the different colors, we can make an SCD analysis and look at the photometry. So here you have J, H, and K band. We only have H band for this data. And here you have the star, the disk, so here the star is 41% of the entire emission. The ring is about 56%. This is the inner emission that we're getting, this alpha factor, which is about 15% of the entire disk, which is pretty significant. It's about 7% of the entire object. And then at the end here, we have this halo component, which just captures all of the larger structure emission that we're getting. And we made an image as well. I won't go too much into it, but as you can see as well, here you have inner emission that we're able to recover. Okay. So one more thing about where inner emission is coming from. So this is one of the theories that we're actively testing at the University of Michigan. So we might be seeing transparent dust grains as well. So those have been seen in AGB stars, if you look at the Noura's paper, and they mentioned that there could be iron-free silicates that are close to the stellar surface within the expected dust sublimation region. So you have things like fosterite or enstatite, which are transparent at the wavelength that we're looking at, and they have been seen in the AGB stars, and we expect them to be seen in YSO disks as well. So polarization work will be really important to be able to look at this and figure out if we're actually seeing that in the YSO disks or not. All right. And then last thing is that we're also doing a Herbig survey in H and K band. These are on top here. These are H band and then K band on the bottom here of Herbig stars. And we've made some images of them to be able to see how often are we seeing this inner emission, so we can really characterize and make this cute little family portrait. And we also started making some models to see what is happening and to try to confirm the structure, to confirm the inner emission, look at the colors, all of that stuff. All right. And then in conclusion, we need a lot more analysis. We want to do more multi-wavelength investigations using infrared interferometry. We want to look at more Chara and VLTI work together. We want to look at all of that stuff and understand how the inner emission works, what the inner edge looks like, pretty much. Being able to look at the SCDs allows us to really disentangle what the emission components are and allows us to figure out what's coming from where. So adding more colors will really help us look at that. I said we're working on a big Herbig survey. We're also working on a T-Tori survey, so hopefully that will be coming soon and will give us a lot more information about what's happening. And then, as I mentioned, there's also a polarization project underway at U of M by grad student Ling Shui. I don't know why I keep saying that. And she'll be able to look at YSO and AGB disks. All right, and that is it for me. Thank you.
I'd like to start by apologizing to Noura for both misremembering and mispronouncing her name. I'm so sorry.
You're good.
It's terrible. Questions?
Bennett Skinner, Master University. You briefly touched on finding a possible rotating feature in this. In earlier talks, we've seen that these rotating features could possibly be associated with planets further out in the disk. Would that be a valid interpretation of your data, or are you not comfortable saying that?
So for the rotation that we're seeing here, I'll go back to it. So the rotation that we're seeing here, it is subcaplarian. It's about half the speed that we expect it to be, just like we're seeing in other disks as well. So it's a lot slower than we expect for it to be a planet. It could be something outside that's dragging it, maybe a planet. It could be like a spiral, something like that. But we don't have enough epochs to be able to really track it. We only have these two. So we don't really have a firm interpretation of what that is. But we do have a monitoring program. So hopefully we'll be able to figure that out soon.
Hi, I'm Takahiro Ueda from CFA. I'm I'm curious about the inner dust emission within the dust sublimation radius. Is there any constraint on the optical depth or dust surface density from your modeling on the inner dust emission?
So in my own modeling, I wouldn't know because we only do like geometric modeling of, so it's like image reconstruction. So we don't really have densities, if that makes sense. I don't do a lot of like radiative transfer or 3D modeling like that. I'm sure other people might be able to answer that better. Yeah.
Thank you.
Artem Agishin from UC Santa Cruz. Thank you for this very interesting work. So as you mentioned, it is possible to have iron-free region inside because the temperature of sublimation of iron and silicates is quite different, and also the kinetics count. So I'm wondering if it is possible to resolve these effects, and instead of having just one silicate line, having multiple lines and multiple levels of dust sublimation, like refractory dust, I mean. If this is something you can resolve.
I think, sorry, can you say that? Like,
Yeah,
like looking at like spectral lines?
Yeah, so for example, yeah, like if you try to image that and then you can observe the alloy melting sublimation line, which is going to be a little bit further away from the actual silicate dust refractory line.
See, so I don't do this work myself, so I'm not sure how to answer that. I don't know.
Okay, we can talk about that.
Yeah.
Sorry, maybe I'm
No.
explaining that wrong.
No.
No, it's good.
You're saying, John is saying yes. It can be done.
If there are no further questions, let's thank Noura again.